Hello, everyone. So it's a pleasure today to introduce Dr. Angie Liu. As you know, she is visiting us from Johns Hopkins, a school that is not long away. She had a short distance, but brought with herself a very heavy and accomplished bag of experiences and a lot of amazing things. As you may know, she has a PhD in University of Illinois, Chicago. Am I right?
Yeah, Chicago.
And also she has spent time at Caltech doing a postdoc. I was familiar with the program. I never noticed that they have the department name Computer Science plus Mathematics.
Yeah,
Computing plus
and
Mathematics.
Mathematical Sciences.
Which I think the title itself tells you that if you're at that place beyond Caltech, you're best to do foundational ML type of research. And that's what she does. She is mostly focusing on robust and trusty AI at this time. I think I had a conversation with her a while back. I was really amazed by the depth and breadth of her insights. Now, some of you may know that I have been also spending some time at Johns Hopkins for a couple of years. Now, I have seen people similar to Dr. Angie at this level of the career, and I've seen the trajectory they had. So we are very fortunate to have her here. It would be even harder to bring her a few years from now. I'm 100% sure she's going to be even busier, more in demand and public. So we are, in that sense, very fortunate to have her here. I think the floor is yours, and yeah, thank you for visiting us.
Thank you so much for the introduction. Thank you. It's my honor to be here today. Oh.
Turning off the lights.
Okay. Oh, okay, cool. So you can see the slides now. Yeah, I'm Angie Liu. As mentioned, I'm from the CS department of Johns Hopkins. Today, I'm going to talk about some recent work for my lab. I titled as Robust Decision Making Under Distribution Shift. So let's first talk about what is sequential decision making. So in this LM era, right? So everyone's talking about agents. And what agent has can be doing is like it can take actions to interact with some environment, and then the environment may provide some feedback and the reward to the agent, and then you can do this again and again in the iterative fashion, right? So you can have a robot, it can be a conversational agent, and then doing that in the real world. And then with LM help, it's currently much more easier to deploy such an agent in the real world. And then a core thing I want to talk about today is something called contextual bandit problems. So thinking about you have a search engine, and then the search engine may be trying to rank some materials for you that and according to relevance to your search. Or it can be a recommendation system. You can also think about it as an agent trying to place some ads and then recommend you with the most relevant product. Or even in most recent days, people also try to use this kind of sequential decision making to study like personalized decision making in medicine, right? So it can be the case that you may have different user may have different reaction to the medicines or some treatment plan, and then you want to optimize for something best suited for these patients. So in all these three cases, you can use a sequential decision making, or more specifically, a contextual bandit problem to model this kind of like interaction between an agent and a user or an environment. So in the first case, the environment is actually the human who can provide the clicks, which is some feedback or some ratings that represent their reactions to some of the choice of the document. In the second case, it can be the case the user is trying to provide some feedback, and also by clicks or by the browsing time, so that the agent will know how useful my recommendation is to the users. And then the third case is like the reactions of the performance of this medicine or treatment on users can show that how good the agent choose the treatment or the medicine for the patients. So in all these three cases, we can use this contextual bandit problem to model the interaction. So some key concept I want to introduce here in this kind of more abstract kind of a scenario, more abstract like a setting, which called contextual bandits, is like a context of action and reward in this process. So then let's use the recommendation system as example. You may go to a website and then you have profile, and that's your context provided to the website, to the agent. And then the agent may give you some kind of recommendation, maybe some kind of like movies or products or ads. And then finally, you may have some ratings, and that's kind of the feedback or the reward as you behave as part of the environment give to the agent, right? So then the contextual bandit problem try to optimize for some maximum cumulative reward. So this you can see happens a lot in our real world. And then when we go to this, in this case, it can be the case the time steps doesn't matter because every time is an independent kind of set of interactions from between the agent and the environment. But also a more famous term these days is reinforcement learning. Reinforcement learning is basically a multi-step version of contextual bandit. You can think about agent take actions, and then you will also see the next state that given by the environment, and then this kind of sequential decision making will give you a trajectory along the different time steps. And the goal for reinforcement learning here is trying to optimize for the maximum cumulative reward during each trajectory. So that means maybe you are interacting with the website for a long time, and they already can learn a reward function along trajectory and fit the best maybe reward function and give you the best recommendation. So distribution shift, as the title of the talk suggests, that we're talking about distribution shift in decision-making problems, may happen in this kind of sequential decision-making under two cases that will be covered in this talk. The first one is like, sometimes you may not have access to the real environment, but you may have access to some offline data. So for example, traditionally, you have some history of interacting with the agent, and that can potentially be used, right? But then there's a shift between your offline data and your real interaction history of the agent. So when offline data be used, there potentially a shift between your login or history and the current interaction. The other case can be like agent need to learn from a slightly different environment when you do not have enough access to the real environment. So that may happen when the real environment is not suitable for doing random exploration, right? So it's maybe very risky for a company to directly try random policy on the users because that may harm their performance, harm their profit. Or it can be the case it's a big cost when you make real random exploration on the environment. It can be the case in robotic system. Maybe it's the device is very safe, very safety critical, and then if you make a mistake, you may break the device, right? So, and then it also can be the case when you have a simulation as a proxy environment. But then the proxy environment is not IID. It's not like exactly the same as a real environment. So in both three cases, you may not have access to real, and you need to either use data or either use a simulation to help you learn this sequential decision-making policy. So that's when distribution shift may happen in the sequential decision-making process. So in this talk, I want to talk about three works. The first two is about the first type of shift, which is like learning from offline data. So we're going to talk about two work. They are both about offline policy evaluation and learning in contextual bandits. And then later, we're going to talk about another work that's extend from bandit to RL, and then we think about the distribution shift in dynamics between simulation and the real environment. So we call that off dynamics RL. And you can see that all of them are under the umbrella of distribution shift in decision making. So let's first talk about the first part, which is offline policy environment in contextual bandit. So let's first talk a bit more about like offline contextual bandit. Why is like needed, right? Similarly, in the previous example, a company may need to do A/B testing, and then but then the environment may not be very available, or it can be the case there's a large cost when you try random policy on the customers. That may harm the performance and the profit of the company. Or there may be very safety critical scenarios like healthcare, right? So if you want to think about personalized medicine as a use case, then the drugs, the treatment on different patients, you just cannot really random try different kind of medicine and treatment on a patient. You always need to concern, maybe there's a lower bound or upper bound of the error that you want to utilize to inform how you can really do this kind of experiment or try different policy with some constraints. So the exploration may not be very safe. Then in these cases, we need to use offline logging data. And this data usually have the structure that you have context, you have some action, and then you have some reward. So this kind of like terminology, let's first be a bit familiar with that. So in this case, you have a tuple of like context, action, reward, and maybe you have n of them. And the problem of off-policy evaluation and off-policy learning for contextual bandits is kind of the problem that given some offline data, I want to ask the question, what's the performance of a slightly different policy? This P, this action given your context is a representation of a potential policy. Policy meaning given a patient or given a customer, I know what to do, I know how to choose the actions. So what's the performance of slightly different kind of policy? Or I want to also answer the question, if I can evaluate what is the performance of the policy, maybe I can know how to optimize for the policy. Can I know what's the best policy given only n tuples of context, action, and reward? So that's our main problem under this offline policy evaluation learning problem. The failure mode here is distribution shift. So the offline policy data usually have this kind of like distributions. Maybe it's like maybe a very biased policy that 80% of the time I will recommend a banana to you, and 20% of the time I recommend an apple to you, right? So these are our logging policy, for example. It can be biased, it can be not optimal, it can be anything, right? It's just like some historical data that I have in maybe in my database. Traditional method usually use impulse weighting to deal with this kind of distribution shift. And then in the literature, it's also called IPS and IPW. It's inverse propensity score or inverse propensity weighting. And the drawback for this kind of traditional method dealing with shift is that it may have high variance, especially when you have like very small data, the variance may be very high. And also especially when you have like very large distribution shift. For example, maybe the logging policy is very biased, like 98% of the time I recommend a banana, and only 2% of the time I recommend an apple. Then you have this very huge weight. Then this also kind of make the problem worse. So this variance of the estimate is something you not want in machine learning. So the key question is like, can we estimate a more robust reward model? Like given impulse weighting maybe is a high variance, then the remedy there is like, can we estimate a reward model instead, right? So because we have like n kind of tuples of like state or context, action, and reward. Maybe I can just learn a better reward model from this n data points. But then it's kind of a classic problem in supervised learning you encountered here as well in offline bandit, which is like when we usually assume when we're learning a model, maybe a classification or regression in traditional ML, you assume trained data is a very good representation of the target or test, right? So that's why in many cases you collect data from some training distribution, you train a model, and then you assume test is the same as training, and then you feel like as long as things are good, my model should perform well in the test distribution. But then it's not the case in real world, right? You may have like different weather condition in the vision problems, or you may have different environment in the segmentation problem. So those problems is very kind of widely and broadly existing in the real world. And here the classic problem of distribution shift still happens in this offline policy evaluation and learning problem. So how to deal with that? We first need to figure out what kind of shift it is. So if you think about our contextual bandit problem, you have like 3 variables, basically, that's important to note here. One is X, which is like our context, maybe your user profile. And then one is action. That's like what kind of maybe movies or recommendation systems you try, recommendation items you try to give to the user. And then this edge between X and A is a mapping between like context and action, right? So what's the policy? Data is a representation of policy. And then both context and action will then lead to a reward function, maybe whether the user liked it, whether the user or the patient have a good performance of the medicine or the treatment, right? So these 3 variables, the relation is like X will determine A, and A and X will determine R. And and we all usually assume this kind of underlying distribution, underlying structure of the distribution doesn't change over time. But what can change is how we'll have a mapping from X to A. That's our policy. In the logging data, maybe you have beta A given X, which is the logging policy. But then in the real learning environment, you have pi, which is a different policy. So this edge may change when we think about the mapping from context to action, right? And then this XA to R distribution usually does not change because real world usually assume that the users have their fundamental interest or preferences doesn't change over time. But that's assumption we can talk more later. It can also change in practice, but we assume it doesn't change. So then it fits the category of covariant shift problem. In covariant shift, we assume that in this X to Y kind of relation, you have PX shift, but the Y given X does not change. That's the classic covariant shift scenarios. Well, in this, when we map to our policy learning problem, we're saying that X and A, the joint distribution will shift because you have different policy in between your offline data and the real data, right? So that conditional distribution changes, then the joint distribution XA changes. But then we're assuming how this user's preferences, user's interest doesn't change over time. So this R given XA doesn't change. So that's a special case of covariant shift we see in this kind of sequential decision-making problems. So when we deal with a covariant shift, I want to introduce a robust regression problem, a robust regression method to deal with covariant shift in the reward estimation problem in offline bandit learning and estimation. And then I want to show how you use this kind of more robust reward estimation in the evaluation and the learning problems in contextual bandits. So that's our outline for the first part. Any questions so far? Okay. So first I want to introduce this framework called distribution robust risk minimization as a tool to deal with distribution shift and covariant shift. So in the traditional ML, we just assume that you have some training data and assume that the data is a good representation of the target and the test, right? But then the distribution robust learning framework is a more conservative framework to say that I do not trust the data. I'm not really sure it really represents my real world. Maybe not, right? But at least I have some data. I can maybe, yeah, I have a question mark there. Maybe I'm not really trusting it, and it may have noise, and then it may be too small, right? Not well representing my target domain. But at least I can use that to kind of construct some feature constraints. And these feature constraints maybe are the features that can represent my data. And then I use that to constrain a adversarial player. Adversarial player is the player trying to do something against you, right? So, and then this adversarial player is trying to play a game, a two-player game with a predictor. So our predictor tries to minimize some loss function, and the adversarial player tries to maximize some loss function under some constraints, which is from our training data, training distribution. So in this case, we're saying the adversarial player can perturb the distribution under some constraints, meaning that constraints meaning we are satisfying some constraints from the future statistics. So that's the key idea, key high-level idea for this distribution robust learning framework. And then when there's distribution shift, this is the math framework that basically represents this framework. It has an objective function like this. So this is probably one of the most math heavy, but also should be okay. Let me explain that. So I have a two-player game, I have a min player and a max player. And then the max player is a Q player trying to maximize the loss function. The min player is a P player trying to minimize the loss function, right? And then you have the Q player also in expectation. The loss function is taking expectation over a maximizer's choice of distribution. So the Q also appears in the expectation. You see the E. And then we're saying the shift happens when we have these constraints for constraining this Q player, which is my training distribution, is from the source. And then it's different from the distribution that you care about in the loss functions. So you think about that, right? So I have my training data, but I do not really care about my training. I care about my target distribution. But then I use my training data to constrain some max player. And then when I take expectation of the loss function, I use a different distribution with target domain. So we're saying I use source data to constrain Q, while I'm directly minimizing the loss function on the target domain, even though we may not have any target labels or test labels in the target data. So that's kind of the key framework. You have to shift between the phi, which is the constraints for the max player, and also the expectation you take over target distribution. And the shift happens and it's a covariant shift. So in contextual bandits, we're saying the context and action is the change in marginal, which is the source data distribution, right? But then in most cases, the policy is the one that's a major contributing factor to the shifts. So you're saying the source distribution is this source context action joint distribution. And then the target X there is the target context action joint distribution for in a real environment when we need to really learn the policy. So this is the offline data, and then that is the real data. And then you're trying to use this minimax framework to get a policy, get the estimation of the reward, not policy, estimation reward, in a robust way. This robustness is about the predictor try to achieve the best payoff of equilibrium in this two-player game while playing a game with an adversarial who is compatible with training data, right? So this constraints make sure the next player is compatible with the training data while the predictor try to win the game, try to play with this adversarial player. So that's kind of the key idea and the notion of robustness when we think about distribution shift in this minimax and distribution robust learning framework. I want to stop here to ask for questions because this is maybe the key framework. Yeah.
So I have a question, like you do the max constraint
Yeah.
on the source data and
Yeah.
the min constraint on the target data, but like are they the same weight? So if my source data distribution, like, but I know that may be impossible, but if my source data distribution is totally different with the target distribution, then like that's a trade-off. But what if the distribution data is different, then what's the result going to be?
I guess you're asking like if the source distribution is totally different, then things may be too conservative. Is that there's nothing similar between these two, then you're doomed basically, right? So we in this case, it's a very good question. In this case, we're still under this kind of covariance assumption, which is saying the conditional does not change, and that's the key part. Because we're still in this minimax, we'll only deal with the marginal distribution changes. So this is the PX target and the P source target here. But then we're not constraining Y given X, and we're assuming Y given X is not changing.
Oh.
So it can so does that answer the question? So the conditional distribution underlying model you want to learn, the conditional, in this case Y given X, is a fixed one.
Oh, I got it.
Yeah. But then I just see a slightly different marginal. And then this happens in offline login policy data, right? My reward doesn't change, the visual reward doesn't change, but I just see a slightly different distribution of the users or the actions in my login data. Yeah, and that constraint is that constraint using that's why you can still use the source data to constrain QY given X because that's still the same conditional distribution. But that's a very good question. Okay, so we're good here, and the definition of robustness is a minimax robustness, a worst case robustness. In this way, you are learning the predictor that's robust to the worst case possible data distribution that can generate this training data. That's the definition of robustness in the first part. So how to solve this game? That's a key question. I skip some of the technical detail, but just present to you some results after you solve this game. So the short story is like when the loss function is a log loss function, and when the phi constraint is a set of affine kind of constraints and convex constraints, you can solve it analytically. So that's the key part. So you have one property is like you have very analytical solution. It's very convenient for learning. So here we're using a loss function that's a relative loss that takes the difference between the p hat, which is a conditional Y distribution you're trying to learn, and a P0, which is a reference distribution. And this reference distribution is kind of the safe default distribution. Because think about you're in a regression problem, when the model is very uncertain, you do not really have a distribution you can fall back to. But then in this case, we'll provide a safe default, meaning that even my data is not informative, I can use a prior to say, when data is not useful, I go back to a default choice. And that's the distribution P0, default choice. And then given this kind of loss function and given the constraints that I find, as I mentioned, you get this kind of analytical form of like solutions for this minimax game. And you have two components. One is the P0, which is your base distribution or prior distribution that's based on prior knowledge. And then the second term is an exponential family based on some density ratio, P source over P target, which kind of quantify how far away your target is from your source. And also some phi function that's your feature function you use, and the theta is your parameters. So you can see that it's actually very similar to traditional logistic regression. The difference here is that you have a default distribution as the prior, and also you have a density ratio source over target that can adjust how much you are confident about your prediction. And that the second part is based on the information from data. And then, as we mentioned, if the information from data is like not much, for example, if source over target is almost 0, meaning my target is very far from my source, then the density ratio is almost 0. Then you can see that second part will just reduce to a uniform distribution, and then you only get the first part. So that means when data is not useful, data is too far away, which is the case that maybe the student mentioned, when there are too large difference, I still have something. That's my prior, that's my default choice, that my safe choice that I can fall back to. So if you have a specific phi function and specific P0, you actually got a Gaussian distribution. That's very convenient. That meaning you can directly predict the mean and variance of this Gaussian without directly predicting the PDF function. So this is because you have an exponential family, and then if the phi function is a second norm kind of function, then you basically get a convenient form. So that's another property of the algorithm. And then, yeah, this density ratio is a key because that can adjust your uncertainty, adjust your confidence based on my density, how far away my data point is from source and from target distribution. Okay, so that's the first part. I will talk about a minimax framework dealing with covariance shift. And then let's see how it can help policy evaluation and policy learning. So in the policy evaluation under general distribution shift and covariance shift, traditionally you usually have this kind of framework. You have the density ratio estimated using both the login data and target data, and then you get IPS. That's your IPS method. You also can just directly estimate the reward function using the login data, and that's your direct method DM. And then these two can also combine together to form a W robust method that basically try to balance these two methods. And then I just listed the analytical form for this two method here. Let's see. And under our framework, you basically have a slightly different mu function. That's the mu function coming from our robust regression. So this mu and that mu in both the direct method and the double robust method is replaced from the traditional linear regression or kind of regression method to this robust regression that account for data shifts. And then we basically can directly plug in this kind of Gaussian distribution estimator, what we get from the previous method, directly to direct method and double robust method. And then the reason why we're talking about also the general shift there is because there are two kinds of shift. One is just the policy changing, or the other cases like both the policy and the context can also change. So we're basically just showing a more general version of a distribution shift. But the idea is like you easily plug in a term in the original direct method and double robust method. So the connection between the previous robust regression and this one is kind of using that to estimate the reward function in the OPE, in the policy evaluation method. So let's see how it works in practice. So contextual bandit problem is actually hard to get data from the reality. So that's why we use a classification problem as and we formulate it as a policy evaluation problem. So the idea is like maybe the context is an image, and then maybe the action is like whether it's a dog or whether it's a cat, right? So it's kind of a distribution over classes, and it can be thought out as an action. And then you may have errors or accuracy in your prediction. That may be regarded as a reward function, right? Think about you have context as image, the action as classification, and the reward as the errors. Then you can just formulate any classification problem as a contextual bandit problem using this kind of strategy. So this is what we do in the experiment. And we look at various combinations of login policy, target policy, and the different kind of shift magnitude. And then here we're comparing with SNIPS, which is a baseline. Think about that baseline, and then you want to be better than it, meaning the curve, the CDI function should be in the left-hand side. The more you are in the left-hand side, the better you have. And then you can see that our method, which is this one, the green one, under the policy shift cases, overperform all the baselines with a large margin, meaning the CDF is all in the left-hand side of the bar, of the 1.0 bar. So that's the relative performance from a baseline in more than 360 scenarios. And then we also look at this is the policy shift case, and this is for the general distribution shift case. We have more than 1,000 conditions for this general shift case. Similarly, you want to be in the close to the left top corner. That meaning is a relatively lower MSE based on a baseline. And you can see that the red one and the green one are from our family, the PS and GCS family, and then also outperform the baselines. So meaning that using a more robust rule function in the offline policy evaluation will help you get a better MSE in general evaluating a target policy in the framework. So any questions up to this point? Okay, so the second part is like how do we use our more robust reward function to do policy learning? So policy evaluation meaning I want to use my logging data to answer a question how good a policy is using this logging data. But then evaluation meaning the learning meaning that given the evaluation, given maybe some reward function, can I optimize for a good policy using this offline data? So the classic framework to do that is called policy gradient. And then in offline setting, it's also the key part you want to pay attention to is also like in the policy gradient, you have another reward estimation, which is the RD log here. And then traditionally you use method to deal with that, but in our case, we want to use minimax robust method to deal with that. So we also replace this reward estimation with our minimax robust reward estimator and see how it works in the policy gradient learning problems. So in this case, we remember our Gaussian distribution from robust regression. We just take the mean of the predicted Gaussian and then plug in the reward estimation function. And then we do a policy gradient on top of that. So it turns out that in this case, we can bound the errors in the gradient estimation. Here, there's a bunch of terms, but the main things like the upper bound is related to some variance and bias of the logging data reward estimation, and some richness of the assumed reward function f, and also some other terms, meaning if you have more data, then you may have a smaller error. So with the benefit of our robust regression method, you can bound the reward, you can bound the gradient estimation using the reward estimation, basically the errors. And also, you can also prove that your policy learning converges over time as well. So this result shows that the policy converges to a stationary point with a convergence rate O1 over n and O1 over square root of n, 1 over t and the square root of n. So t is the time steps and n is the number of examples you have in offline data. And so that means it's kind of as you can show, it converges over time if you use our reward estimation in policy gradient. And then we also look at the experiment on some more standard like classification problems in CFAR10, MNIST, and OPT digit. And the red curve is our method that have the regret much lower than some of the DM, IPS, DR baselines. So we can also see if you have like online exploration, not just offline, but you use offline as a starting point, and like doing transfer learning, you can start from offline estimator and then do the online exploration. You can also do this kind of like more two-stage learning for policy learning. And then we can also achieve like a much fast reduction of reward, which is the red line here, comparing to some of the baseline method. So the conclusion for the first part is like we introduce a robust reward estimation method. Remember the minimax framework and then the covariance shift discussion, right? And then we use that to estimate the reward. And in the offline policy evaluation and learning method, so that we propose this distributed robust learning offline policy evaluation and learning. And then you can see that when we deal with shift, when the reward estimation is more robust, it can help the estimation and help the learning, offline learning performances in both pure offline and also offline plus online kind of like exploration settings. So that's the power of like a more robust reward estimation and in the sequential learning and the sequential decision making process. So that's the first part of the talk. Any questions up to this point? Yeah.
Wonder how on the standard data set, how did you mimic the problem by tracing the data?
Yeah. That's a very good question. So we talk about you can use the standard classification data set to mimic or simulate a contextual bandit, right? Then when we try to simulate policy shift, then you will need to have a different classification rule. Basically, you can, for example, sample a subset of data and train a bias classification rule based on that. And in the case, it has some errors and it's not perfect. That's okay. But then you just train a different kind of logging policy, or logging policy in this case, meaning a different classification rule that is different from the target classification rule that you have. As long as they're different, you can kind of control the bias by how heavy you train the classification rule in the logging data. You can also generate, you can also simulate that. Let's say maybe I have a rule-based classification rule that maybe I predict cat 80% of the time, I predict dog 20% of the time. That all can be controlled when you are generating your own kind of logging policy. Yeah, that's one way. That's only the policy shift. When you try to consider the context and action shift together, you can also subsample or bisample a different kind of distribution of the images. Maybe you try to have more cats than dogs in one case, but then you have more dogs than cats in another case, and that's kind of simulating the shift in the context space. But yeah, when you have this kind of scenario, it's easy to control the target policy and logging policy to simulate the contextual bandit offline problems. Yeah. But for sure, this is just a simulated cases. We're looking forward to have some real world data, for example, in medical or in self-driving car, like when you really have like the real world like off policy problems, maybe you have some logging data and onto them and adapt to target. That would be very interesting. But here it's a method paper. We mostly just use simulated cases. Yeah, but that's a very good point. Any other questions? Okay, so let's go on. So the second part, I want to talk about this alpha dynamics RL work, which will go beyond bandit, which is only a independent kind of every time step is independent. That's assumed in the bandit case, but in RL that's different. You may have this temporal dynamics. That's the effect of temporal dynamics need to be considered. So in alpha dynamics RL problems, we assume that maybe the interaction, the real world environment is not easy to get, but we at least can have some simulations. For example, in the Mars rover case, maybe you cannot directly do exploration on Mars, but you may have some simulated environment on Earth, and then you can still do this interactions with the simulated environment. Or in robotic surgery, in Hopkins, we have those built platform for simulation for surgery tasks. They're not perfect because you can see that the background and also the anatomy is like very simulated, but at least it can help you get a sense what will be the real environment, and still want to utilize those kind of environment to help you learn a good policy for the real world. So then in the off-dynamics RL case, we'll assume the source domain and target domain have different dynamics. That dynamics here meaning the transition probability. So let's take a look. So we're assuming two MDPs. MDP is the Markov decision process. You can think about it as just the P distribution over of ST plus 1 given STAT, meaning given the previous state actions, what will be the probability of the next states? And we're assuming that the source distribution and target distribution, they are not the same. So this conditional distribution S given SA is not the same, but we assume we have the same reward function. So the reward SA or SAS, they're the same. The only thing that's different here is the MDP. Again, it's a simulated and more abstract problem than real world, but it's motivated from the sim to real transfer. Our goal here is trying to learn a policy in the source domain with limited access to the data to target domain. But then you want to maximize the reward in the target domain. So we do not have a lot of access, but we will have some access to the target domain. But mainly we're using the source domain data to help me learn RL policy that will generalize to a target domain. So that's the setup. So a previous method is called dark. Maybe it's not. Yeah. Okay, but DARC, dark. So the idea of the dark is that you try to match the distributions of trajectories of the policy in the source domain and the optimal one in the target domain. So that sounds complicated. So let me decompose that a little bit. So usually in RL, you can write down the policy distribution over distributions. The policy distribution over trajectories like this. So Q function is all the distribution of trajectories in the source domain. That's a product of the initial states, and also the dynamics of the source, and also some policy pi in the source, right? So that's my distribution of source trajectory. And then the target distribution of optimal policy, optimal distribution over the target trajectory is, you can assume that since it's optimal policy, then the policy pi star should in proportion to exponential of a summation of the reward. So that's an assumption, that's an intuitive assumption saying if my policy is optimal, and that means higher reward, higher cumulative reward will lead to a more probable action, right? Then I basically can write down the distribution of target trajectories under the optimal policy as this. So P by target is, again, the initial distribution, the dynamics versus target dynamics, and now have exponential of this cumulative reward, which is the pi star, instead of pi theta, pi star. So they have these two distribution trajectories. And then the previous method tried to reduce the gap between P and Q. They assume that maybe the P and Q are not that far away, then I should be able to match or align those two distributions. So that's the key idea. So how should you make sure the P should be similar to Q? You try to measure the Kell divergence of these two distributions. And it turns out that you can reduce the Kell divergence to three terms: a source cumulative reward, a delta R term, and a entropy term. So I want you to focus on the second term, which is delta R. This delta R is actually, after derivation, if you trust me, is the log probability of target minus the log probability of the source. So meaning if I know there are two dynamics, then I can use log probability, the difference between log probability to measure a term that's delta R, they call that. And then you can use that in the first formulation to minimize the Kell divergence and learn a policy such that distribution trajectories are similar between two domains. And then it turns out that the R can be estimated using domain classifiers. You can decompose this conditional probability into two joint probability, and then take the base rule. So here you have two classifiers. One is about the couples, SAS. One is about the pair, SA. And then just learn two domain classifier and use the probability of these two classifiers to together estimate this delta R. And this delta R is called the reward modification. The orange and blue are two classifiers. So thinking about how you think about two distributions now, you just collect a bunch of data and then use the tuples and the pairs of SA and S, and then try to learn the differences using domain classifier, meaning I learn a classifier to classify how probable my data is comes from the source domain and how probable my data comes from the target domain. So we have only 10 minutes. Okay, I'll speed up. So the limitation of this method is that you can learn a policy that generates the same distribution of trajectories, but that does not mean that you can directly deploy this policy to target because can I remove this?
It's going to be just a few seconds. Yeah.
Okay, so
Yes.
maybe I'll come back to this plot. Yeah. Okay. So when you deploy the same policy that generates the same distribution, because you have like target domain and source domain dynamic shift, you're not going to get the exact distribution trajectories after you deploy the policy because this high theta is learned using the source domain, not using the target distributions. So key question is like, even though you match trajectories, doesn't mean the policy is matched. Maybe I can go back to this. Yeah. So you match trajectories in the state distribution, but then doesn't mean the policy distribution is matched. Because MDP is different, you still have a gap there. So what we propose is to try to utilize the distribution learned by Dark, which is the previous method, and then try to mimic the state distribution, but not action, so that I really learn a policy that can generate the optimal target distribution trajectories in the target domain, not in the source domain. So the idea we call it DARA is domain adaptation and reward augmented imitation. It has two components. One is still the dark training, the previous method, but then we augment the imitation learning component to mimic the distribution trajectories from the dark policy. So, and then it has also it's a kind of GAN formulation, have discriminator learning and also generator learning as well. So you first have some target domain data, very limited. It's only used for reward multiplication, this delta R learning. And then after you learn a policy that should give you a distribution of trajectory that you want to mimic, you use this as experts data to give a supervision to imitation learning. And then again, you interact with the source domain to try to mimic this distribution, this green arrow. And the way to mimic it is try to learn two networks. One is a discriminant network that try to differentiate my fake policy and my true policy. It's kind of, again, classifier learning. And then another component is the imitation is a generator kind of network to try to generate policy data by interacting with the source domain. So it's again kind of a framework. You have a generator, discriminator, but then the supervision data comes from a dark policy that mimics the original target distribution of the optimal policy. So this kind of framework, we show that it significantly improves the performance of dynamics RL. So we also have some self-analysis. Here, you can ignore some of the notions here, but you have three components basically. One is like the better you learn dark, which is the first component in the left-hand side in the previous slides. The better you learn that, the better, right? So, and then later you also need to estimate errors in your imitation learning, and it has approximation error and estimation error. Approximation error comes from the function class you use to learn the discriminator. And then the estimation error comes from the number of like samples you may have, but altogether it's like the imitation learning error bound. You can bound you can guarantee that if you learn good dark and if you learn imitation good imitator, then you can get a good policy, so of dynamics like RL performance. So I'll quickly skip this. And then when you think about the error analysis and error bound for thinking about our method and the previous dark, one thing is like we do not assume some of the assumptions in the dark paper. The dark paper assumed that the optimal target policy is lies in some of the set, and this set they call then no exploit set. And this set is kind of saying that the scale divergence between P source and P target is smaller than some epsilon. So that means the previous work only works under the assumption that if your optimal policy reduce or induce the same kind of set of trajectories between these two domains. Meaning if these two domains are very different, the optimal policy of the target does not really induce the same distribution, then it breaks this assumption and then the previous method will not work. So the meaning here is that experiences for any policy in this set are similar in the source and target domains. And if it's not, this can be violated. So in our method, we try to avoid this kind of assumptions with this kind of imitation learning component. So we are kind of more flexible when we try to use this imitation learning to mimic the dark policy. And it can be the case that we do not need the optimal policy of a target to really in this set. So that's more flexible. So in the experiment, we try to look at Mojoko, the very classic RL simulation framework, and it includes, for example, half-cheetah, walker, reader, and a richer, and then a hopper, this kind of like environment. And then we try to create some shift in terms like either you change gravity or friction, or you change the environment to be like maybe certain action of the Mojoko is broken. For example, when you have hopper and walker, maybe some joint is like disabled. Then, and you still want to be able to learn using those kind of broken environment. The question here is like, first, can we, does dark suffer performance degradation, which is our assumption? The other thing is that whether our method can outperform the baselines. So let's first see the first part. We show that dark, which is the previous method, if you look at the dark evaluation and the optimal in target, which is the comparison between the first column and the third column, you do see that it's far from the optimal in target, even though it tries to mimic the target optimal policy, right? So it's true that dark evaluation is worse than the training and also worse than the optimal in the target domain. Well, in our case, we try to, this is the last column is our method, and this is the cumulative reward. And in all four kind of environments, we try to see that compare with the baselines. The first one is basically, the first one is similar with dark because it's without imitation learning. And then you can see that with and without like imitation learning, you get a big difference. In some of the environment, the difference can be more than maybe 10 or 20% of the reward. So our method with this imitation learning component do outperform other baselines, especially outperform the dark, which is only the reward augmentation, reward modification method. So let me see. So conclusions here, the previous dynamic RL works suffers the performance degradation. We identify issues and try to propose a machine learning component to mitigate the issues. Relax one of the previous assumptions, which is you need to have the experience very similar between these two environments, and we are more flexible than that. And our method can work in more general shift cases and scenarios. One thing I want to mention is also the previous rule do not really work in the gravity and friction or embodiment and transfer domains. They only work in the broken environment domains, while in our case, it can be more general. So to conclude that this talk, we talk about offline learning, policy learning problem in connected bandit, and also of dynamics problems in RL. So we're under the umbrella of like shift under the sequential decision-making problems. But there are many more problems like that, and not just dynamics different or policies different, right? So we can further talk about how about we have a more dramatic shift in online policy learning, and then not offline, but online when the policy changes over time. Or it can be the case, how about we look at constraints in the learning problem, meaning that you do not only have shift, but you also have safety or cost upper bound that you want to satisfy in the learning process. That's also something you need to deal with in many real applications, not just offline, you have offline and online. And how about we look at more severe domain shift? So we only talk about the dynamic shift here, but maybe the background is different, maybe the lighting condition is different, maybe the whole environment is different, then there are many shifts that can happen at the same time, then you may need a new method to deal with that. So last I want to attribute the contribution to my PhD student. Yuhao is currently my student working in those of dynamics RL problems. Hao is currently a student in Caltech, and then Zhou Hao is also in Hopkins.